Welcome you all for the day two of the mini course by Professor Mahan Maharaj, which is part of the Introduction to Topology mini course. And the third lecture today will be on what is hyperbolic geometry. And the moderator for today is my another colleague from ISER Pune, Professor Mainak Podar, who is both a topologist and geometer himself. And he will take care of the question and answer moderating for both Zoom and YouTube. And like yesterday, we have our student volunteers, Akash Gupta, who will be taking care of the YouTube streaming, and also our other students, Priya Singh and Divya Shri. They will be taking care of the questions. Priya will take care of the questions on YouTube, and Divya Shri will take care of the questions on the Zoom meeting. Take care in the sense they will help Mainak address the questions asked by the participants. Okay, Mainak, over to you now.
It's a great
Yeah.
pleasure to introduce Professor Mahan Maharaj. Uh, Tejas already gave a very formal introduction uh, about him yesterday, so I'll not repeat all those things. But Professor Mahan Maharaj is a very eminent geometer and topologist. He is internationally acclaimed for his works on hyperbolic geometry, on geometric group theory, low dimensional topology, complex geometry, etc. I find that his way of thinking about things is very fascinating, and it's a privilege to chair this session. So, with these words, I hand over to Professor Mahan.
Thanks a lot, Mainak. Thanks, Anisha, for this opportunity to be here at the IWM series of talks. So, as I said yesterday, we spent yesterday introducing topology, and today we will be introducing geometry as very closely related to topology. So this particular, the subject that we will be introducing in the first lecture is hyperbolic geometry, and in the second lecture, we will be again bringing you reasonably close to what is going on at the cutting edge. Okay. So I'll try to introduce what hyperbolic geometry is about. Yeah, today, the first lecture. So what is hyperbolic geometry? And the best place to start is is to ask even a more basic question: what is geometry, as we see in the introduction to geometry in schools? Yeah. So, so we start studying geometry with Euclid's axioms. And so, what are these axioms? The first axiom says that any 2 points in a plane may be joined by a straight line segment. Yeah. So the first axiom, when it talks about straight line, it really means straight line segment. And the second axiom says that a finite straight line segment can be extended continuously in both directions to a straight line. So typically, it's this is the second one. What it's referring to is referring to a bi-infinite straight line, and the first one is talking about a straight line segment. Yeah. So what is it that you really need to define a straight line segment? It's just a pair of points. That's all it means. The third basically says it defines a circle. So a circle can be constructed on the plane with any center and any radius. So these three axioms, in some particular sense, what they are doing is they are introducing the players in the game, yeah, of Euclidean geometry, or for that matter, any geometry. Anytime you have a geometry, these players need to be there. And so straight line segment, bi-infinite straight lines, and circles. The fourth axiom basically says that all right angles are equal to one another. What does that mean? So the thing is, a right angle needs to be defined in terms of the players that have already been introduced. The thing is, a right angle can be defined in terms of a straight line. So what does it mean? It means you take any straight line and any point on it, and then you bisect the angle that goes from the positive direction to the negative direction. So this half of the angle on a straight line from the positive direction to the negative direction is what is called a right angle. Yeah? Does not mean that all other angles are wrong, but this is really the basic angle that we need to play with. It's two lines where the second line bisects the angle on the first line. And what is this axiom saying? It's basically saying that independent of the bi-infinite line you started off with and the point you chose, the angle that you get is something fixed in magnitude. This is the meaning of the statement that all right angles are equal. So a right angle depends on two pieces of data: A, a bi-infinite straight line; B, a point on that straight line. So these are choices you make. The fourth axiom says that the angle that you get is independent of these choices. Now we'll introduce, so again, so what have we introduced so far? Straight line segment, bi-infinite straight line, circle, angle, yeah, particularly right angle. I mean, this fourth axiom is the basis of all the measures of angles that you see. A protractor or all other instruments for measuring angles is based on this particular axiom. But now we'll introduce something that it's an axiom, but it really has a different status, and therefore it goes under somewhat different names. So this is how this particular axiom has a different status. What does it say? It says that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles, which means you have a transversal, you have two lines falling, so two lines which are cut by the transversal, and suppose that the internal angle on the right side the sum is less than less than 180 degrees, less than two right angles, then they will, if extended, meet on the right side. This particular axiom turns out to be equivalent to what came to be called the parallel postulate. It's equivalent. It's also equivalent to the statement that the sum of the angles of a Euclidean triangle is 180 degrees. So around 100 BC, it was observed that this fifth postulate is equivalent to the parallel postulate, which basically says the following: take a straight line on a plane, take a point not on that straight line, then through that point, there is exactly one and only one straight line through the point parallel to the given straight line. What does parallel mean? It just means that the two straight lines never meet, however much you extend them. And Euclid posed this question: can you prove somehow or the other, this is really talking about a property of parallel lines. Yeah. It's not really defining players in the game. The first four axioms were introducing players in the game. The fifth is declaring a property of parallel lines. And so its status is different. It's a property which is being introduced in a somewhat ad hoc way. And the problem that was posed is does this property follow from the notions of the players in the game? And the attempt to prove the fifth postulate from other postulate is what gave rise to hyperbolic geometry. And there are very few problems in history, the history of mathematics, which have had this kind of rich background. It took basically 2,000 years to solve this problem. So the attempt to prove the fifth postulate from other postulates gave rise to hyperbolic geometry. So what is the history of the problem? Gauss started thinking of parallels, say, in the late 18th century, And in the early 19th century, to his friend Taurinus, he wrote the following. The assumption that the sum of the three angles of a triangle is smaller than two right angles. See, as I said, the parallel postulate is equivalent to the statement that the sum of the angles is equal to 180 degrees. What Gauss is saying here is that you replace that axiom by something that violates that axiom. The sum of the angles is strictly less than 180 degrees. What he says is that it does lead to a geometry, meaning it obeys the first four axioms I talked about, but the properties of parallel lines are different and it is a consistent system of geometry. So what it's saying is that it's smaller, it leads to a geometry which is quite different from our Euclidean geometry, but which is in itself completely consistent. And for various reasons, Gauss did not publish his work. But really, the discovery of hyperbolic geometry is due to Gauss. And observe the dates, 1824. And the first, and Euclid is 200 BC. So really, it's something like 2,000 years that it took to solve this question. There's a reason why it took so long. The reason is basically, see here, this is a kind of a logical conundrum here. What it basically says, I mean, what was the way that the question was formulated? The question was formulated as, prove the parallel postulate from the remaining axioms of Euclidean geometry. What this solution is saying is that you replace the axiom by a sharp negation. Instead of saying that the sum of the angles is equal to 180 degrees, you replace it by the axiom sum of the angles is strictly less than 180 degrees. And what it's giving rise to is a consistent system of geometry, which means that if you introduce the parallel postulate as in Euclidean geometry, you get a consistent system of geometry. You replace the parallel postulate by a strict negation, sum of the angles is strictly less than 180 degrees. Then also you get a consistent system of geometry, which means that the axiom, neither the axiom, or well, maybe let's put it positively first, both the axiom and its negation are individually consistent with the remaining axioms of Euclidean geometry. Or, and from that what one can deduce is that neither the parallel postulate nor its negation can be derived from the remaining axioms of Euclidean geometry. Okay, good. So this was the problem. And so now what we'll do in the rest of the talk today is we'll dwell on how this happened, but a little more on the history. A whole bunch of people actually have attempted this problem. So I'll just mention a few names. Lambert introduced what we call hyperbolic trigonometric functions in the 18th century, and in today's context, he computed what is the area of a hyperbolic triangle. And then in the 19th century, hyperbolic geometry was extensively explored by two mathematicians, János Bolyai from Hungary and Lobachevsky from Russia. And this problem, I mean, this kind of geometry is often named after Lobachevsky. Okay. Is there any intuition behind replacing the axioms? Okay, fine. Okay, Manik has taken care of. Great, terrific. Yeah, so Manik, if there are any questions you would like me to address, just call my attention to it and I'll do the yes. Okay, great, terrific.
So Mahan, there is a question asking, can you explain how to construct such a triangle? I guess you are going to address.
Sorry, you're a little.
So yeah. There is a question saying, can you explain how to construct such a triangle? I guess you are going to talk.
How to construct such a triangle? Yeah. I'm just saying that what Gauss proved, and then we will actually construct something very closely related to a triangle. After the construction, you'll see that you'll be able to construct the triangle. Okay, good. So I'm just leading up to the problem, leading up to the solution of the problem. So Bolyai and Lobachevsky worked on it. Lobachevsky published a paper called On the Principles of Geometry in 1829. Oh, what's going on? Yeah. So Lobachevsky published a paper called On the Principles of Geometry in the 1829-30, and Bolyai very soon after, in a different paper, Absolute Science of Space, he discovered the same thing. The term hyperbolic geometry, it was not called hyperbolic geometry at that time. Yeah. The term hyperbolic geometry was introduced by Felix Klein in 1871, and a marked development happened in the late 19th century with the advent of Poincare. Yeah? And the kind of hyperbolic geometry that we know today is essentially all due to Poincare, and that's the treatment that we will be giving later on. Yeah, basically, I mean, it took a fair bit of time for it to get refined and get connected to the rest of mathematics per se, and that's all really due to Poincare. Okay, with this much history behind us, let's go back to the mathematics per se and revisit the problem. So what's the problem? This is try to deduce the parallel postulate from the remaining axioms of Euclidean geometry. So what is the parallel postulate? We've stated it in one form. Two straight lines, if they are intersected by a transversal, make an angle, sum of internal angles less than 180 degrees on one side, then they'll meet when extended on that side. And here's the parallel postulate, which is an equivalent formulation. Says, given a straight line L in a plane and a point X on the plane lying outside L, there exists a unique straight line L prime lying on P, passing through X and parallel to the line L. This is the parallel postulate. Given a straight line, given a point outside it, there is one and only one line parallel to the first line through the point. Okay, good. And this is Euclid's problem. Prove the parallel postulate from the other axioms of Euclidean geometry. And the solution, as we said, turns out to be that it can neither be proven nor disproven. Yeah. So it needs one to probe deeper. And so really what we need to ask is, these things that have been stated in Euclid's axioms, they need to be inquired into first. So what are the players in the game? And we are asking for a more fundamental explanation. So first, and this is really the most important question, when Euclid plays this game, he takes for granted that we are doing planar Euclidean geometry. But there is nothing that defines the plane. So we need to ask, what is the background of this question? The background which was taken for granted needs to be inquired into. And this is a standard kind of theme in mathematics, where you not only look at a question or a problem, but you really inquire into the background from which the question comes, the background in which the question makes sense. And once you start inquiring into the background, then the context of the question becomes clearer. And once the context becomes clearer, you can address things better. So the basic question is, what exactly is this plane P? Yeah? This plane P, which is taken for granted by Euclid and assumed as a background without further explanation, needs to be understood. And without understanding this background, this context, one cannot answer this question. This is a basic point. And so, based on a more fundamental notion or fundamental definition of a plane, we need to understand what straight lines are in this context. What is the notion of parallelism in this context? And here is the definition of a plane that we will be looking at. And so what exactly is Euclidean geometry? It is done in a background plane, R2, which is equipped with a metric. And the metric is given by this simple formula, a package, ds square equal to dx square plus dy square. What it really is, it's an infinitesimal form of the Pythagoras theorem. But one thing that you should mark here is that somehow or the other we have introduced very quickly a fundamental and rather deep concept, namely that of an infinitesimal. The notion of an infinitesimal was nowhere on the horizon when Euclid posed this question. And a really satisfactory answer to this question, what is a plane P, can really be given in terms of this infinitesimal notion. And this is really it's really Newton, yeah. So you really, I mean, to even and Leibniz. So Newton and Leibniz much later, yeah. So you've already covered something like close to 1800 years, and calculus has been introduced. Without this context of calculus, I mean, the initial notion can be one can play around with in a flat piece of paper. But unless we have a more fundamental understanding of what a flat piece of paper is, what the plane is, it's very difficult to answer these questions. And so you really needed the introduction to, I mean, you needed calculus to be introduced in order to have a really more satisfactory context in which the questions can be posed. So what does infinitesimal calculus mean? It really means that this formula in itself is really just a meaningless bunch of symbols. What it means is actually a package. It gives you a way of computing lengths of curves. What are lengths of curves? What are curves, firstly? They are smooth maps of the closed interval 0, 1 into R2. And they are computed as per the formula. Length of a smooth curve is the integral of 0 to 1 ds. Yeah. So this ds is an elemental length of an arc. So how do you do it? You basically parameterize the curve x equal to xt, y equal to yt for this curve sigma. Yeah. So it's a parameterized curve now. And then you look at the derivative of x with respect to t, dx dt. You take the derivative of y, you get dy dt. So dx now becomes dx dt times dt, and dy becomes dy dt times dt. You apply the infinitesimal Pythagoras, which means you take dx dt square plus dy dt square and take the square root. And then you have an integral with respect to this single parameter t, and you integrate from 0 to 1. Yeah. So what the Euclidean plane equipped with the metric means is that it assigns for you, by this formalism, a length to every smooth curve, every smooth curve. So at one stroke, what it is saying is that you have a way. What is Euclidean geometry? It is something that allows you to compute not only lengths of straight lines, which is what Euclid started off with, distances between points. It really allows you to compute lengths of any smooth curves. This is key. And it's all packaged in this one little formula, ds square equal to dx square plus dy square, which is an infinitesimal form of the Pythagoras theorem. Good. So once you have this formalism, we try to explore the other questions that we had asked. What is a straight line? What are parallels? And here's the thing, straight line segments really enjoy a distinguished status in the context of this particular metric. They are the unique paths that realize the shortest distance between points. Yeah. So basically, what are we doing? We are replacing, we have understood now a plane, not just in the naive way that Euclid looked at it, but in a more fundamental sense, as a way of packaging lengths of all curves, not just straight line segments, but then that has removed straight line segments from the picture. They are reintroduced as some things that have a particular special feature, namely that they are the shortest distances. They are the paths that realize the shortest distance between a pair of points. Good. What about parallel lines? You just take two of these straight lines. If they don't meet, that goes back to Euclid again. We don't have to do anything new with it. Two by infinite straight lines are parallel if they just don't meet. That's all. Okay, good. So once we have looked at this, we have this formula, ds square equal to dx square plus dy square. If we are to attempt this problem and we look at this particular feature, if we define our Euclidean plane to be ds square, it's R2 equipped with ds square with this distance, ds square equal to dx square plus dy square, then the fifth or the parallel postulate does follow. So if you take as your definition of a plane this more fundamental notion, ds square equal to dx square plus dy square, way of measuring distances, then it is true that given that the parallel postulate is a consequence of this metric. So what Euclid's question now translates to after this introduction of calculus is whether this definition of the Euclidean plane is inevitable from the remaining four axioms of Euclidean geometry, or can they be relaxed, which means that the point of attack for the problem is now determined, and it is this simple formula that we looked at last time. As basically asking, can you relax this formula or is it inevitable from the remaining axioms? So let's try to play around with this formula. That's all you need to do. You need to play around with this formula so that the remaining four axioms of Euclidean geometry are satisfied, and then ask, what are the shortest paths in this modified geometry after you've played around with them? That's really now the problem. So the point of attack for the problem took so long to determine. And this point of attack was, people were actually playing around without determining it. So, and this is how a lot of deep mathematics is done. You identify the point of attack, where exactly is the real problem. Yeah. And once you've identified that, you can start playing around and try to address your questions. Okay, good. So let's start playing around. Suppose I want to modify this geometry. So I want to play around with it. I want to modify this notion of a distance. So I want to modify Pythagoras' theorem in infinitesimal form, in its infinitesimal form. What do I want? So what do? I replace. So the thing is, when I write dx square plus dy square, there's another thing which is implicit. It's basically the fact that dx square has a coefficient which is 1. And dy square also has a coefficient which is 1. But these coefficients are not really numbers. That's the second piece of understanding that's there. These coefficients are really functions, and the functions are really the constant function 1 defined on R2. Yeah, that's the second point that we need to understand, that really in this formula, which packages the lengths of all curves, ds square equal to dx square plus dy square, it's actually dx square has a coefficient which is the constant function 1 defined on all of R2. Don't think of it as a number, but think of it as a function, and that will be a proper understanding. So once you realize that, then you can replace the constant function 1 by a positive function. All you want is lengths are positive, nothing else. So you replace this formula and you modify 1. This number 1 has to be modified. So you take ds square equal to f, a function of xy, dx square, plus a function of xy, g of xy, dy square. All you need is that the functions are positive so that lengths given to curves are positive. And then you have the modified length, modified package which assigns new lengths. What is it? It's basically 0 to 1 ds. And how do you do it? To the same parameterization, f of x t y t dx dt square plus g of x t y t dy dt square whole square root dt. And then you integrate that out. And you replace f and g by the constant function 1, you get back infinitesimal Pythagoras, from which the fifth or the parallel postulate does follow. But now you are asking, well, suppose I replace this by arbitrary functions, positive functions f and g. Do the same axioms hold? The first 4 axioms are reasonably easy to check, at least locally. Yeah. Existence of straight line segments and extensions, I mean, with very mild assumptions, you can satisfy all these axioms. But what about the fifth postulate? Now the problem has become a different problem. The first part was really, we really had to probe deeper into the structure, and we were asking fundamental questions. What exactly is the plane P? So it's, one of the, perhaps the most universal geometer alive today, Misha Gromov, French-Russian mathematician. There are 2 kinds of ways of doing mathematics. One is energy intensive, where you dig, yeah. And the other is minimize entropy, which means you find the correct direction when you have zillions of directions available to you. The first part of this problem was really digging and excavating the structure, the more fundamental structure underlying Euclidean geometry. And that's what gave rise to this notion of calculus, the notion of infinitesimal, and this notion of integrals of curves, of lengths. So finding lengths of curves through integrals. Now we have a different problem. Now, instead of a problem of poverty, no clear idea of what a Euclidean plane is, we now have a problem of riches. The functions f and g can be chosen from this uncountable basket. Yeah. Any positive smooth function really works, but there are zillions and zillions of them. How are we going to choose the correct function? If the functions were inevitable, then Newton would have solved problems, solve Euclid's problems, or somebody around that time. Why did it take Gauss close to another 100 plus years from the discovery of calculus? Why did it take Lobachevsky or Polyai? And the real answer is that from all these infinitely many functions, you have to choose your function judiciously. And that's what the rest of the problem is about. Yeah. So here, let's just revisit what are straight lines in this geometry and in this modified geometry. So what is it? We now introduce, since we have modified the background, we need to replace the notion of straight line by something more general. And this is a word, it's called a geodesic. Given 2 points, x1, y1 and x2, y2 in the plane, equipped with the modified metric, the geodesic between these 2 points is the unique path that realizes the shortest distance as per the previous formula between them. Second, an isometry is a map that preserves the metric, which means the following. If it takes xy to x1, y1, then you look at the formula on the left side, which is f of xy dx square plus g of xy dy square, which is the square of the infinitesimal length. And what this says is that you change the variables x to xy to x1, y1, then the same infinitesimal length is preserved. F of x1, y1 dx1 square plus g of x1, y1 dy1 square is the same as the length of an infinitesimal segment before the change. Yeah. So in Euclidean geometry, you had all these things which we learned, SSS congruency, angle-angle side congruency, SAS congruency, etc., etc., right angle hypotenuse side congruency. All these are basically saying that there is an isometry which takes the first triangle to the second triangle. So what Euclid is doing, without introducing this notion of calculus, he is introducing a whole multifarious notion of congruences between triangles. But with the introduction of calculus, what is happening is that there is this simple notion of an isometry which packages all these multifarious congruences together into a single package. It's basically just something that preserves infinitesimal distances. Yeah. So you've introduced a structure, infinitesimal notion of a distance called a metric. And what we are doing here is what are the maps that preserve this extra structure, and those maps are called isometries. And we need to understand what are straight lines in this modification. Those are geodesics. And then you say simply that geodesics are parallel if they never meet, if they can be extended by infinitely and they never meet. So now, again, let's revisit the question. We have this choice of infinitely many functions, f and g, and we want to make a choice of a function, f and g, judiciously. That choice, that informed choice of f and g out of these infinitely many is what gave rise to hyperbolic geometry. So all that hyperbolic geometry will be is a particular choice of these functions f and g, and they will be defined not on the entire R2, but on a naturally chosen open subset of R2. Because so what we are needing is building is basically a model. Yeah. So a model for hyperbolic geometry, the subset that you're looking at is the upper half plane. It's x comma y with y greater than 0. It's the strictly open upper half plane. And the metric is dx square plus dy square, but divided by y square. Note that it means that as you approach y equal to 0, the metric starts blowing up to infinity. And of course, this is the one place in this particular talk where I have done a bit of a pulling a rabbit out of a hat. And the real question is, what made somebody focus on this particular metric? That is a completely different story. It came from a related but not quite the same field of mathematics. In fact, it was not regarded as related at that time. And it's the genius of Poincaré, which basically came up with this natural object. This particular plane this model is called the Poincaré upper half plane. Yeah, it's the upper half plane equipped with this metric is named after him. So Poincaré had this strange habit, perhaps unduly modest, of discovering things himself and then naming them after other people. Yeah, not after him. I mean, of course, nobody names it after oneself, but it's. I mean, he assigned names. So, for example, I think he assigns. He was studying some differential equations which were first explored by Fuchs, and he came up with a notion of a geometry and symmetries groups. He called them Fuchsian groups. Then Klein said, no, he had discovered them. He said, okay, fine, I'll discover stuff in one dimension higher. And he discovered high dimensional guys and named them after Klein. So the story is that Fuchs had nothing to do with Fuchsian groups. Klein had nothing to do with Kleinian groups. And Poincaré had everything to do with both. So fortunately, there is some justice in the world. So subsequent mathematicians have named the Poincaré upper half plane after Poincaré. So this is the upper half plane. And we need to understand, as we said, okay, so we've defined this metric. It comes It's a lot of it is inspired by complex analysis. And in this particular field of geometry, complex analysis and hyperbolic geometry, they go they go hand in hand. And there is a theorem which says that there is an exact correspondence. It's called the Poincare-Coebeck-Klein uniformization theorem, which goes between the complex analytic way point of view and the hyperbolic geometry point of view. This is just an aside to say, but basically that much of mathematics is really a unified whole. And here we are really going to be looking at this ds square equal to, this metric on the upper half. Good. So what are we wanting to do? Once you have equipped the plane with the metric, we need to understand what the straight lines are in this geometry. And so we need to understand what are the geodesics in this geometry. What are the paths which minimize distance? And the first thing is that vertical straight lines in the upper half plane are geodesics. Vertical straight lines minimize paths, and in fact, the vertical segment between a pair of points on the same vertical, it is the unique geodesic between those 2 points. What does that mean? So you look at 2 points, and for convenience, I'm just looking at the x coordinate as fixed 0. So you look at a path from 0y1 to 0y2. And then what are you doing? You have dx square plus dy square root divided by y. See, dx square plus dy square by y square was ds square. So what is ds? In order to integrate, what are we trying to integrate? ds over sigma. So ds is square root of dx square plus dy square by y. Yeah. So which means what? X prime t whole square plus y prime t whole square. Yeah. Square root of the whole thing, dt, yeah, divided by y of t. That's what we are wanting. But then you remove one of those square terms, which means this x prime t whole square dt square is removed. Because it's a square, it's a positive term. So the length is going to be the length of this path is always going to be greater than equal to dy square root by y. But dy square root is just dy. So really integral, oh, I should have written an integral sign here. Integral of dy by y from y equal to y1 to y equal to y2, yeah, which is exactly log of y2 by y1. Log of mod y2 by y1. Oh, sorry, actually it should be mod log y2 by y1. Okay.
So Mahan, there
Yes.
is a question in the chat, sir, why only the upper half plane will be equivalent if we take right half or left half planes with certain metric?
Yeah, sure. So if you change the metric and you flip, as I said, there is an isometry of the left to the right by choosing the appropriate metric. So you choose the x and y coordinate, you're going to get the right half plane. So that's not, yeah. This is a convention, and it's just a convention. It'll basically allow x to vary. We prefer x to have full range and y to have half the range. That's all, nothing else. Okay, so we found one particular theorem. We found that the vertical straight lines are geodesics. Good. Why? Because if you take any other path which deviates from the vertical, you're going to get something which has length which is strictly bigger. And this length, this minimizer, is going to be realized only when the first term dx square is equal to 0, which means dx is equal to 0, which means x is equal to constant, which means it's a vertical line. Good. So we found one collection of geodesics in this, the vertical lines. And then what we are going to do is we are going to find new geodesics, but those new geodesics are going to be obtained from these simple naive guys that we started off with. So next thing is that translations. And here we take a translation. It's translation in the x direction. So xy goes to x plus a comma y.
Sorry, there is one more question on the YouTube chat. Is asking, is the length minimizing paths the same as energy minimizing paths for a particle traveling one point to another?
The answer is yes. The answer is yes. The thing is, it depends on what you mean by energy. And here what we are really doing is you're looking at the square, right? It's dx dt, I mean, it's dx dt comma dx dt inner product plus dy dt, I mean dx dt dy dt vector, tangent vector, inner product with itself. Yeah, that's the energy. Yeah. And that's really what you're minimizing. There is a different way of thinking of geodesics, which is not what we have gone into here, which is essentially the acceleration along the geodesic is zero. That also gives you another equation, and this is a variational way of looking at geodesics. But here the thing is all very naive, yeah. And I mean, really, yeah, these are different ways of looking at it, and there are more sophisticated formulations of geometry where these notions start differing. For those who know this whole thing, it's basically introduction of a Riemannian connection allows one to make sense of the statement that acceleration along a geodesic is zero. Yeah. And energy minimizer is basically this length square minimizer. And that's, yeah, I mean, the tangent vector captures for you the energy. And in this particular context, that can be generalized further. But that will take us very far afield. It will not really illuminate this particular discussion. So let's stick to what we were discussing. And we had this one vertical line through the origin. And now we check that f of xy equal to x plus ay, yeah, which means just translate along the x-axis. Then what happens? That x1 is equal to x plus a. Then dx1 is just exactly equal to dx by our notion of isometry. Then d of x1 is equal to dx. dy1 is equal to dy because y1 is equal to y. So dx1 square plus dy1 square by y1 square is equal to dx square plus dy square by y square, according to this formula. So which means basically translations along the x direction are isometries. Hence, from this one simple special case of the vertical line through the origin, you get all verticals are geodesics. But there's a little more. And this is really what helps us. And this is the one place where there is one little simple computation to be done. It's basically, this is the statement, inversions about semicircles. This inversion is, again, it's basically spherical reflection. It comes from spherical optics, which was explored considerably by Fermat. So what is it? Define the map from the hyperbolic plane to the hyperbolic plane, which takes Z. Now, complex coordinates are helpful. This is the only place where a little bit of complex analysis helps the computation. And it gives a hint as to why complex analysis is related to hyperbolic geometry. So you take Z and you send it to R square by Z bar, where R is greater than 0 and Z bar denotes the complex conjugate of Z. The theorems, I mean, it's a simple observation which says that G actually is an isometry. We'll do this computation. Yeah. So G is an isometry of H, and therefore, what does it mean? That we can now use these new isometries to take images of these simple geodesics that we've already discovered, namely these vertical straight lines, and look at the images of these guys under isometries, and then we'll get new geodesics. Why? Basically, if a point, if a line is the shortest distance between a pair of points, you act on it by the isometry, the image of the geodesic is going to be the shortest path between the images of the points. So images of vertical geodesics under inversions will be geodesics. So if we can prove that this inversion about semicircles is an isometry, we will potentially have a new class of geodesics, new class of straight lines in this modified geometry. So let's do this computation. What I'll do is I'll just set capital R is equal to 1 because it's just a bit of a clutter. And we can do, I mean, all the entire idea is contained in this computation with r equal to 1. So we change everything to complex coordinates. dz is equal to dx plus I dy. dz bar then is equal to dx minus I dy. And what is the real metric? It becomes dx plus I dy times dx minus I dy, which is dx square plus dy square. And then what is y? Y is equal to z minus z bar by 2. So dx square plus dy square by y square, which is the real expression, is exactly the same thing as minus 4 dz dz bar by z minus z bar whole square. Yeah, I mean, there's this 2I in the denominator, which squares and becomes minus 4 upstairs. So let's do this. I mean, the coordinates are better. I mean, the complex coordinates are better adapted to polar coordinates, and the inversion, the flip, is really more natural in polar coordinates. So what is the transformation? You're really doing reflecting along a semicircle, a fixed semicircle with center at 0, radius 1. So what is happening is that the angle theta, the argument, is remaining fixed, and r is changing to 1 by r. So what is happening? So this is an example of an inversion. R comma theta goes to 1 by r comma theta, where you're inverting about a semicircle of radius 1 and center 0. So what does z go to? Z goes to 1 by z bar. What does z bar go to? 1 by z bar bar, which is 1 by z. So what does dz go to? Just apply the chain rule. Minus 1 by z bar square dz bar. What does dz bar go to? Minus 1 by z square dz. Now just plug all this in. dz bar is going to minus 1 by z bar square times minus 1 by z square dz bar dz. And what does z go to? It goes to 1 by z bar minus 1 by z minus z bar whole square goes to 1 by z bar minus 1 by z whole square. Yeah. So in complex coordinates, you plug all these transformations in, and you notice that in complex coordinates, the metric remains unchanged by this transformation. This complex coordinates actually makes life much simpler, and you just plug it in, and it's just this one simple computation with this background. And then you notice that inversion in a semicircle preserves the infinitesimal form of the metric. In particular, it is an isometry. So hence, inversion is an isometry. And what did we say? Now, since you have an isometry, you look at images of straight lines under this isometry. But this is the only, so far, whatever we have done, this is calculus and a little bit of complex analysis, or calculus with complex analysis. Now, the rest is good old Euclidean geometry. What is the image of a straight line under inversion? And so this big semicircle passing through D is the semicircle about which we are inverting this straight line, which is tangent to it through one endpoint. Yeah? And claim this is a Euclidean geometry exercise. This vertical straight line, when inverted about the large semicircle, it gives me the small semicircle, which is tangent also to the original line, but it passes through the center of the bigger semicircle and meets the boundary of this upper half plane, namely the x-axis, at right angles. Why is this the case? And the idea is basically similar triangles. So assume that the point at which the semicircles meet the vertical line, call that O. Then what happens is that the triangle OAC and the triangle OBA, these are similar triangles. And from this similarity of these two triangles, I mean, it's basic Euclidean geometry, nothing else. The angle in the semicircle is a right angle. So angle OBA is a right angle. And because the vertical line is tangent to the semicircle, angle AOC is also a right angle. From this, you get these triangles are similar. And from that, what do we get? You get that the length of AB times the length of AC is equal to the length of AO square, which is the same as the length of AD square. I mean, that's the radius. And what was AD? It was 1. It means basically length of AB times the length of AC is equal to 1. So this flip R to 1 by R, which sends C to B. Yeah. Yeah. So the flip, because length of AC is equal to 1 by length of AB, it means that inversion about the semicircle through D sends C to B and B to C and keeps the origin. I mean, it's, yeah, the semicircle is centered at the origin. So A goes off to infinity, infinity comes back to A. Yeah. And along any line through A, you look at the point at which it hits the vertical. That point is going to be sent to the semicircle inside, which means that this smaller semicircle through A and B is an image of the vertical line containing C inverted about the semicircle through D, and therefore the smaller semicircle through A and B is a geodesic. Nothing special about A and B. All the properties that we have are you take any semicircle on this with which meets the boundary x-axis at right angles. Take a larger semicircle, double the size, with center at one end point, radius equal to the diameter of this first semicircle. Draw a vertical through one end point and invert that straight line. You are going to get back the semicircle you started off with, which means what? In the hyperbolic plane, you now have a whole bunch of geodesics. We've already started off with vertical straight lines are geodesics. And what we've now argued is taking semicircular arcs with center on the real axis, which means basically meeting the real axis at right angles. These guys are also geodesics. It's not hard to see from the basic fact that straight lines, the vertical straight lines, are the unique geodesics between pairs of points on the same vertical, that these are all the geodesics in your plane. Yeah, we don't need that. But we have now a very large collection of geodesics, vertical straight lines, and semicircular arcs with center on the real axis. But now suppose you're given one straight line, which means take a vertical line as our standard object. It's a vertical straight line. Take a point outside it. Yeah, just take a point outside it. And the question was, how many straight lines are there through that point which are parallel to that vertical straight line? Which means how many straight lines are there through that point which do not meet the original vertical straight line? Certainly the vertical line through that new point is. But then there are semicircles which pass through that point and do not meet the original vertical straight line. How are we going to do that? Take that point, join it to any point on the straight line by a line which does not intersect your vertical line. Bisect that line and draw a semicircle with center at which the perpendicular bisector of that straight line segment hits the x-axis. And this new semicircle is going to be a semicircle centered on the real line which does not hit the vertical. And so we get the new parallel postulate, which says the following: given a geodesic in L, which means the vertical line, and a point X on H lying outside it, what have we constructed? There exist infinitely many bi-infinite geodesics L prime lying on the upper half plane H, passing through X and not meeting L. Euclid's axiom, what did it say? It says there is one and only one straight line. What are we saying now? There are infinitely many geodesics through this point which do not meet the original guy and therefore are parallel to the first one. Yeah. So what have we shown? That there is this new parallel postulate which hyperbolic geometry defines. And in fact, if you replace the parallel postulate by this new parallel postulate, then the system of geometry that you get is hyperbolic geometry. I think I'm more or less in time. I'll stop here. Thank you very much.
Thank you very much, Mahan. So, a lot of claps. So, is there any question from anybody?
Only one axiom. Okay, hang on. Why? What was this question?
Oh, there is a new...
Somebody. Why only? Yeah. Since modular forms are also defined on the upper half complex plane, and since, as you mentioned, there is a correspondence between hyperbolic geometry and complex analysis, I would think that hyperbolic geometry gives a natural framework for modular forms. Could you maybe comment on this relationship of modular forms, possibly even on the more arithmetic aspects of modular forms and hyperbolic geometry and complex analysis? Yeah, indeed, there is a very close relationship between modular forms and hyperbolic geometry. So basically what one does is the following. There is, I mean, you look at the collection. I mean, so what are isometries of the upper half plane are exactly the same as complex analytic isomorphisms of the upper half plane. Yeah. So that's basically given by Z goes to AZ plus B by CZ plus D. That's if you can actually, from these inversions, you look at the orientation preserving isometries, that's exactly equal to the group of Mobius transformations. Z goes to AZ plus B by CZ plus D, A, B, C, D, real numbers, yeah? Which is exactly the same as real Mobius transformations, which is the same as 2 cross 2 matrices SL2R quotiented by the center PSL2R. Yeah? So PSL2R, these are, I mean, yeah. So that's Mobius transformations, and so if the entries are in integers, so inside SL2R you have the integer matrices. These are the SL2Z matrices. Yeah. And then you look at the quotient of the upper half plane by SL2Z or PSL projected by SL2Z more precisely. What you get is the modular surface. So the modular surface has both a hyperbolic metric and it's equivalent to a complex analytic structure. So what are modular forms? There are natural complex analytic line bundles over this. And then you look at sections of these line bundles. Those are exactly modular forms. This is it. You look at, here what one is doing is looking at hyperbolic geometry. I mean, so from a hyperbolic geometrist point of view, what are we really doing? You look at the modular surface, which is the quotient of the upper half plane by a particularly nice group of symmetries or isometries, namely SL2Z. Quotient out, you look at this modular surface, look at its real tangent or cotangent bundle, look at its tensor powers with itself, and then take sections. Yeah? Those are exactly modular forms from this point. And there is this, the point is that the Euler class turns out to be even, so you can take square roots, and those are these things where half figures in the modular form. That's it. So yeah, I mean, certainly modular forms and these guys were, the hyperbolic geometry is extremely closely related. I should point out that modular forms were introduced way after Ramanujan gave his incredible predictions about how they should behave. No idea about, I mean, even modular forms as a thing came much after him. And I think in a certain incredible way, he had a sense of how they behaved without even the structure being laid in place. Okay, good. So that is one collection of, so this modular forms question address. There was some other question.
Yeah, there is one that says, are there any other geometries where either of the other four axioms is not
Mainak, if you can move can you come to speak closer to the mic? I can't.
Okay, sorry. So uh, uh, there is a question: are there any other geometries where either of the other four axioms is not satisfied, but the
No, the first four actually, I mean, we'll have to define a geometry as something, right? I mean, geometry is just a word. So the first four axioms are somehow or the other fundamental. Fundamental meaning without those, the notion of a geometry doesn't quite make sense. There are some modifications of that where a bi-infinite straight line segment need not be extendable infinitely. These are called incomplete geometries. So there's a theorem called the Hopf-Fredo theorem, which basically says that you look at pairs of points and then minimize distances over all possible paths, and what you get is a metric in the usual notion of a metric space metric. That metric that you get is complete if and only if the axiom of extendability of straight line segments to bi-infinite straight lines is there. The thing is, without a notion of a metric, a notion of a geometry does not make sense. And the first geodesic, it's not even, I mean, you can relax it still further. So the first axiom, which is the existence of a straight line segment minimizing distances between pairs of points, a system where that is satisfied, is called a geodesic metric space. Yeah, so sure, you're just going to introduce new words by relaxing various things. That's all. A notion of a circle is what? It's a collection of points at a fixed distance from a fixed point. Yeah, that's it. And then there are notions where the notion of an angle can be relaxed and better things can be found. I mean, more general things can be found. Yes. So the short answer is yes, but the long answer is depends on the context.
So there is a question, sir, where we need hyperbolic? Maybe what it means is what are the applications or something?
Fantastic. Fantastic. Great question. Wait for 40 minutes or half an hour, whatever.
Okay. Yeah, so there are, both these questions seems to be related to application of hyperbolic geometry. And there is one question on YouTube. Is geodesics and displacement the same terminology?
No. Geodesics are replacement of straight. I mean, this is a Euclidean geometry question.
Yeah.
What is a geodesic? A geodesic is basically a shortest path, right? Yeah. So replace. Okay. So is a straight line in Euclidean geometry the same as a displacement? No. A straight line segment does not have a direction. It's just a distance minimizer. Displacement is movement along a direction. The most efficient way of displacing is along a geodesic. That's maybe the connection. How to measure angles? Take inner product. I mean, this notion of a metric actually gives you a way of measuring angles infinitesimally. Yeah. So you take two vectors in the tangent space, so the metric actually gives you the inner product between those two. So a more general form of an angle is really this inner product, and the metric gives you a way of measuring angles via this inner product.
More questions. Is there a reason why it's called hyperbolic? Does it have anything to do with hyperbola?
Yes, it does have something to do with hyperbola. This is a good question. So what you do is the following. You actually look at three-dimensional space, dx square plus dy square, but then you flip one sign. So you look at a metric where the quadratic form can possibly give you even negative length. So you look at R3 equipped with dx square plus dy square minus dz square is equal to is equal to ds square. And now you look at the unit sphere in this, which is what? It's dx square plus dy square minus dz square equal to -1. Yeah. So sorry, not dx square. X square plus y square minus z square equal to -1. So that's or equivalently z square minus x square minus y square is equal to 1. Yeah. So z square minus 1 is equal to x square plus y square. That's the hyperboloid of two sheets. Restrict the metric dx square plus dy square minus dz square to one of these sheets, to the hyperboloid. So it's not related to the hyperbola, it's related to the hyperboloid. And when you restrict this metric, it's called a Lorentz metric. So when you restrict the Lorentz metric to the unit sphere in this hyperbolic metric, namely the hyperboloid, then what you get is a different model for hyperbolic geometry, and the metric on that sphere turns out to be isometric to the metric we described on the Poincare half plane. That's the connection to hyperboloids. Yeah.
Next question is, please suggest some references for beginners to study hyperbolic geometry.
I think there's a book by Stilwell. Or maybe there's another book which is a nicer book by Ratcliffe, John Ratcliffe.
It's Ratcliffe.
Yeah. Ratcliffe, I think, or maybe FF, just F.
Yeah.
Something like J. Ratcliffe, as far as I remember.
Next question is about sum of angle in triangle. Hyperbolic geometry, will it be always strictly less than 180 or can be strictly greater than 180?
No, it's always strictly less than. That was Gauss's observation, right? That's what we said. The sum of the angles will always be strictly less than 180 degrees.
And
is it the Euclid's fifth postulate only that differs Euclidean geometry and hyperbolic geometry? I mean, in this formulation, yes. Okay, good. Lots of very nice questions. I'm very happy that there's some people. Can we characterize groups that act on the upper half plane more informally? Wouldn't that be asking how can we move around in the upper half plane? Yeah, exactly. This is the isometry group of the upper half plane. And that, as I said, the orientation preserving isometry group is exactly SL2. It's 2 cross 2 matrices. SL2R quotiented out by the center, which is plus minus the identity, which is called it's projectivized SL2R. And the way you identify it is basically by this transformations, Mobius transformation, Z goes to AZ plus B by CZ plus D. Yeah, this is it. This is the right book, Ratcliffe.